This is a run through of the mock quantitative PSA for A2, which the title is Investigating the Vertical Oscillations of a Mass Hung from a Spring. To speed things up a little bit, I've already drawn my table on the board here. I've done a little bit of the setup already. What I've done is clamped a ruler onto one clamp here, and I'm going to set up the other one now, which will hold the spring. Now I don't have to do much lining up here because on the diagram all I need to do here is displace it about 4 centimetres if you read the instructions. So as long as I can see roughly 4 centimetres when I hang my masses onto the spring. Now what I need to do is hang 200 grams on my spring, like this. And the bottom of that is coming down to 22.5 centimetres. I need to displace that vertically by about 4 centimetres and allow it to release it to allow it to perform the oscillations, and then record measurements to accurately determine the period of the vertical oscillations. So, stopwatch here. I will measure the time taken for 10 oscillations, hence on the table 10t up there, and then I can divide that by 10 to work out the time period. So we'll displace about 4 centimetres. And okay, that's 5.25. I'm going to verify that by repeating that measurement. I'm just waiting for it to reach the bottom part of its oscillation, roughly at my marker on the ruler. So that's a fiducial marker, roughly. Okay, it's 5.34 seconds. So oscillating. So average. That's 5.30 seconds. Now, that's my 10t, so I need to divide that by 10 to work out the time period. That's 0.5. And what I've done is written 0.530. That is carrying forward the significant figures from the raw data to my t-value. So if I state again, my average time for 10 oscillations was 5.30. That's 3 significant figures. So I can state my time period to 0.530. The alternative is to use my reaction time, and this is relevant for the very next question, where I have to justify the number of significant figures I've used for t. So my first option is to justify the use of 3 significant figures. There are 3 significant figures in the raw time, so I carry forward the minimum number of significant figures, which was 3, to my time period. Second method, use reaction time. So if I write my t values to one decimal place, I would then have two significant figures there, and I would carry forward the two significant figures to my time period value. So in that case, it would be 0.53 seconds. Either of those methods of justification is fine. So that's my first value that I can put into my first set of data that I can put into my table. So that's 0.200. Now increase the mass to 300 grams. I need to take a range of measurements now for masses of 200 to 700 grams. So I'm going to do 200, 400, 500, 200, 300, 400, 500, 600, 700. So this is 300, and you take the measurements in the same way. So I'll just do one more set of data before I speed things up and just take it off camera. That's 6.56 seconds. I'm going to repeat. .63 seconds. You'll notice possibly when I'm taking the measurements, I close one eye. When taking measurements where I'm trying to see something happening in the X or Y planes relative to me, and where Z plane would be going away from me or towards me, the accuracy of your eyes is improved if you close one eye in that regard. So looking sideways and up and down. So that's why I close one eye. 6.63. Take some more measurements. 400 grams. So displacing it 4 centimeters. Release. And I'm waiting for it to come down to the bottom part of its oscillation before I start the timer, and then I count for the number of oscillations from then. Okay, so we've got 7.53 seconds. I'll repeat that. .40 seconds. So I've done 300 and 400 there. In addition to that, I need 3 more sets of data, so I'll do 500, 600, 700 off camera, and then come back once I've got the data. I've now got all the data from 200 to 700 grams. Working out the averages and doing some calculations. Before I do that, as I was going along, I got some values such as this one here, which I thought, well, I'll just double check this value here. This is 8.91. The first reading was 9.12. I thought I'd just verify that one. As it turns out, it wasn't a good reading. So when I redid it, I got something a little more consistent. 9.06. So as you go along, it's a good idea to just be aware of anything like that. And if you do get a similar reading again as the one that you think might be a little bit out, then that's fine, you stick with it and proceed. So my averages, retaining the same number of decimal places as the raw because it's the average of the raw. 6.60, 7.47, 8.21, 9.63. Divide these all by 10 to get my time period, and I'm just carrying forward the significant figures here. So these would be 0.660, 0.747, 0.821. That's the advantage of doing 10 oscillations, just divide it by 10. Those are my time period values. Just move this to the side here. Now it's calculating the logs. This is log base 10 that I'm using, not the natural log. So log of m divided by kg, 0.2. So that gives me minus 0.69. That gives me 0.6989, but I'm rounding up to 3 decimal places here. I've got 3 significant figures in my m. That needs to be converted into decimal places in my log value. So 3 decimal places here. You can increase the number of decimal places by 1. So I could have 3 or 4 decimal places here, but I can't decrease them, so I can't have 2. Now, given that it's 3SF to 3dP, and this 3dP happens to be 3SF anyway, most people didn't make mistakes here, so should be alright. The rest of the values, 0.523, 0.398, 0.301, 0.222, 0.155. Right. Then same thing for log t. These are 3SF also, so 3dP in here. Can do 3 or 4. I think I may have bunched mine up too much, no? That is my completed table now. So the following task will be to do the graph. Again, what I'll do, because this will be on the graph paper, I'll have to change the angle of the camera to get an idea of what's going on with the graph, and maybe just do snapshots of that to speed things along also. So I'll finish this section here.